So in the second part of chapter 16, I want to quickly review thermodynamics. So remember, thermodynamics deals with the energetics associated with our reactions. We're going to talk a lot about free energy in organic chemistry, oftentimes called Gibbs free energy. Gibbs free energy has a relationship with those equilibrium constants that we were talking about in the previous section, where our free energy is going to be equal to negative RT ln of K. Remember, R is equal to our gas law constant. We'll be using the value of 8.314 joules per mole times Kelvin, since we need our R in units of energy, which is joules. T still represents temperature. Please remember, temperature needs to be in the absolute scale, which is the Kelvin scale. And again, that capital K is going to be our equilibrium constant for the reaction that we are dealing with. Another way that we can calculate free energy is also by knowing the enthalpy and the entropy of the reaction. So free energy can be equal to the change in enthalpy minus the temperature times the change in entropy, where again, temperature would need to be in the absolute scale. The reason we want to deal with these absolute scales is because our sign on free energy is what's going to be important for us as we start talking about the energetics of a chemical reaction. And if delta G is less than 0, it tells us that we have a spontaneous reaction as written. It's an exergonic reaction, and that the products are going to be more stable than the reactants. So it's a favored reaction. If our delta G is greater than 0, we have a non-spontaneous reaction as written. It's an endergonic reaction, and the reactants are going to be more stable than the products. So really, it's not a reaction that is favored, and we would have to supply energy in order for the reaction to run. The enthalpy that we just previously looked at to calculate free energy, remember, enthalpy implies heat energy. With our heat energy, we can talk about things being exothermic or endothermic. So if our enthalpy is less than 0, we have an exothermic process. This means that we are losing heat energy to the environment. If our delta H value is greater than 0, we have an endothermic process, which means it is absorbing heat energy for us. The entropy that we looked at is delta S, and this is really just a measure of disorder, so how disordered things are. Remember, the natural tendency for processes or for spontaneous processes is for the entropy of the universe to increase. So that is one of the ways that we can look at defining spontaneity of reactions if we define the entire entropy of the universe as increasing. So entropy very generically defines for us the measure of disorder within the system. For most of what we're going to be dealing with, that delta S becomes negligible. We really don't see much of a change in terms of states of matter, in terms of the number of molecules that we're dealing with. Most of our organic reactions are nicely 1-to-1-to-1 ratios, and things pretty much stay in a liquid state or a solid state as we go through the process. So most of the time for us, that delta S is negligible, which means that our free energy is going to be equal to the heat energy that we have. So we will oftentimes use either the enthalpy calculation or the free energy calculation to help us define the overall energetics associated with our chemical reactions. We are going to be using free energy diagrams to help us represent what is happening with our chemical reactions. So for our free energy diagrams, we would be looking at energy on the y-axis. With our free energy diagrams, remember we're talking about Gibbs free energy. So this is oftentimes also represented as our delta G values that we're going to be looking at. The x-axis becomes our reaction coordinate. So basically it can be looked at in terms of time. It can be looked at as the reaction progresses. It could be looked at as bonds are being broken, bonds are being formed. So we oftentimes just generically call this our reaction coordinate. In our energy diagrams, we always start with our reactants and the energetics associated with them, and we're going to end with our products. And the first one that I am going to look at is going to be an exergonic reaction, which again implies for us a spontaneous reaction, and the products are more stable, so they're going to be lower in energy than the reactants. But one of the things that we go through for every single reaction is we do have to go through what we're going to call a transition state. This transition state is going to be a high energy state as part of this elementary process of going from reactants into products. The transition state represents that bonds are being broken and bonds are being formed, which is why it is such a high energy state. It's the process of going through bonds broken and bonds formed. So it really contains what we call partial bonds. They're not true bonds, they're not completely formed or completely broken bonds, which means we cannot isolate this transition state. It is something that we derive theoretically. If we run reactions well enough, we can start to get glimpses of what these transition states look like, but we cannot isolate this compound. It's not a true compound, it's not a true molecule, and we cannot isolate it when we talk about these transition states because they are such high process or high energy things that we will be looking at. So through this free energy diagram, there's a couple other areas that you need to know as well. The amount of energy from the reactant up to this transition state is what we call the free energy of activation. Basically, it tells us how much energy we need to have to overcome the reaction itself. Every reaction will have this free energy of activation, this energy that we have to initially input to get the reaction started or to get the reaction going, even for something that is exergonic, something that's going to release energy in the process. The abbreviation that we would be looking at with this would be our delta G under standard conditions with the double hashtag. So this implies for us our free energy of activation. The amount of energy from the reactants down to the products, this would be our calculation for our free energy. So that would be the value that we would be looking at for delta G for an exergonic reaction. I also want to look at an energy diagram for an endergonic reaction. So remember, in an endergonic reaction, our reactants are more stable than our products. So the reactants are lower in energy than the products. With this diagram, we still have a transition state. So we still have that energy barrier on the high energy species that is higher in energy than both the reactants and the products. What we're going to be looking at here is our free energy of activation is much larger because the reactants are such a low energy species, that free energy of activation becomes much larger in an endergonic process than an exergonic process. The delta G of the reaction, so the energy associated with the reaction as a whole, part of that will be the free energy that we would be looking at. So these would be our two relationships between the exergonic and the endergonic processes when looking at free energy. What you will want to notice and what we'll be looking at in the future is kind of where that transition state lies in relationships to reactants and products. If it is closer to the reactants, it will look more like the reactants, so that would be more of our exergonic reactions. If it is closer in energy to the products, like it is in our endergonic reaction, that transition state will look more like the products. So knowing the type of reaction that we have, exergonic or endergonic, can also help us define a little bit what that transition state will look like, what bonds are going to be broken, what bonds are going to be formed through this process or through the actual mechanism itself. So you want to get used to drawing these free energy diagrams. We will start talking a lot about them and putting them in relationship with the mechanisms that we will be drawing in the future chapters.